Okay, time to start the second talk of the morning session. So Semen Shlosman will tell us about how to see the KPZ fluctuations and Tracy-Widom in the Ising model.
Right. Tracy-Widom is with question mark.
Tracy-Widom with a question mark, that's
Yes,
true.
yes. So for those of you who heard parts of that story, I apologize because it's a long story spanning a couple of decades already. So I hope I am in the audience where I don't need to remind you a lot about what the Ising model is. So it's a random field on the lattice. So we have random variables taking values plus minus 1. And then we have the Hamiltonian of a configuration, which is minus the sum over sigma x, sigma y. X and y are neighbors. And then we want to consider a probability distribution on those sigmas, which is given by exponent of minus the inverse temperature times this Hamiltonian. Okay, so this expression does not make much sense, but we will not need. One can explain what that precisely means, but we will not do it. We will, for our purposes, it would be enough to talk about the Ising model in large but finite box, and for that reason, we say it like that. We take a box of size n, and then we have some boundary condition outside our box, and we have some running configuration inside. And then we make another definition. We say that the energy of sigma v given the outside is given by more or less the same sum, x and y, sigma x, sigma y. Now x is in Vn, and y is just a neighbor of x. So in that sum, the sum is taken over all nearest neighbor bonds, which are inside V, and also bonds which are inside and outside. And in that case, we put here the value of this boundary condition. Okay, and then what one need to know about the Ising model, that in 2 dimensions, that it undergoes a phase transition. The transition is manifested in the following way. If we apply, so maybe I write another line here. So now we can talk about the distribution in this Vn, given this boundary condition, also the temperature, the inverse temperature of sigma, that is now equal to the exponent of minus beta h sigma given sigma bar. And now to make it into a probability distribution, we should normalize by the partition function, which depends on the temperature, on the parameter n, and on the boundary condition. Now this is a well-defined probability distribution, and we will talk about this Gibbs distribution for large finite boxes. And the nice feature about the Ising model is that it undergoes phase transition, which means that if the temperature is below the critical temperature, and we do this construction, and we apply it to 2 different sigma bars, so here my sigma bar is exactly identically plus 1, and here sigma bar is identically minus 1, then we will have 2 different probability distributions, and those probability distributions would be different no matter how large n would be. Namely, the typical configuration under that probability measure looks like this. We have C of pluses, and then occasionally we see islands of minuses. So it's like that. And here is the opposite. So here we see C of minuses, and with islands, small islands of pluses. And this picture, that picture survives the thermodynamic limit. If you take n to infinity, still the two measures would be different, provided the temperature is below the critical one. And while if we, so those two probabilities are not equal if the temperature is small, which means that the inverse temperature is bigger than the critical beta. And if the temperature is above the critical temperature, then the boundary conditions have no influence on what we will see inside in the thermodynamic limit. So we have this phase transition, and that's what makes one of the many reasons why the Ising model is a Drosophile of the statistical mechanics, as some people put it. So, okay. So this picture is, one can say it differently, that there are two phases for the Ising model, the plus phase and the minus phase, and they are really quite, they are qualitatively different. In particular, we can compute the mean value of the magnetization if we can introduce the sum Mn, which is the sum of sigma x, x belongs to Vn, then the expected value of this with the plus boundary conditions at the temperature which is below the critical is equal to some constant, some positive constant, times n squared plus terms of linear order in n. Okay, and this function m of beta is positive, provided beta is bigger than beta critical. So it is this is called spontaneous magnetization, and this function spontaneous magnetization is positive if and only if the temperature is below the critical temperature, which in other words, beta is bigger than beta critical. Okay, so this is a reminder, and then so this picture tells us that you either see the plus phase or else you see the minus phase, but we would like to put them, to have them in the same picture. And for that reason, what we do is that we restrict our consideration to the following auxiliary situation. When we take a plus phase, but we consider only the configurations such that the magnetization of those configurations is equal to, as I told you, m star of beta times m star of beta times n squared. But on purpose, I put here some positive constant. And I want to, so by this constraint, I force my configurations inside to have much more minus spins than it typically would like to have. So one might expect that if I constrain my distribution P plus to such configurations, one would see maybe just a lot more minus droplets here to compensate for this extra A. But no, this is not the correct picture. those minus droplets, they don't like to be separated, staying like that. So they instead form a big droplet of minus phase. So like the quicksilver would do if you have many droplets of quicksilver on the table. So you will still have some small droplets of minuses, but you also will see a huge one also, droplet of minus phase. So inside it looks like a minus phase with small islands of pluses. And outside we see a plus phase with the small islands of minuses. So by putting this such a constraint with this A positive, we then force a droplet of the minus phase inside our box. Well, one should be a little bit careful. This is not exactly precisely what would happen. This picture you will see with large probability. And this large probability would go to 1 when the size of the box goes to infinity. So at a finite n, of course, you can see any picture. But you want to know what are the typical picture. Typical picture is such that you will have just a single droplet like that. And moreover, that single droplet is not just some arbitrary random shape. It has the asymptotic shape. To find the asymptotic shape, one has to solve some variational problem. The variational problem one needs to look at is the following. One should introduce the surface tension. This is a surface tension. For the two-dimensional Ising model, I will not tell you how you introduce it. It's just a function on a circle. It's a positive function on a circle, on a unit circle. And then what you should do with every curve gamma, you should associate the corresponding functional, which is the integral along gamma of what? Of you take at a point S of your curve gamma, you compute the normal vector. Then you take the surface tension of that normal vector. Then you integrate over your gamma. So your gamma is a loop. And then you minimize this functional. Then you minimize this W of gamma over gamma such that the area of gamma is equal to 1. And then you get certain curve. If the surface tension would be just a constant, it will be a circle. But in our case, when the surface tension does depend on the direction, you will have some curve like that. So this is called wolf shape. So it's a limit shape for that random droplet here. And the meaning of that statement is the following. If you take this limit shape, imagine this is a unit square, so to say, and then you expand it so that it would fit your random shape here, like that. And then you optimize how you put the two of them on the same picture, and then you compute the fluctuations here. You will find that those fluctuations are of square root of n. Okay, so those are just Gaussian fluctuations, and this is how in that sense, this random droplet has the asymptotic shape of this non-random wolf shape here. So as n goes to infinity, you will see that this random object would more and more look like some nice smooth curve. And this theorem was proven long time ago in a book by Roland Dobrushin, Roman Kotetsky, and myself. Okay, so this is all preliminaries, and then the real story I want to talk about starts when we start to play with this parameter A, and then let us see what will happen when A increases. When A goes to, okay, just increases. So if A increases, then this droplet also has to grow, right? And at a certain moment, see, before that, this position of the droplet is random. It can be anywhere. It doesn't like to touch the walls of the box, but otherwise it floats somewhere inside. But when A grows, then it becomes bigger and bigger, and then as a result, what you will see that part of its lifetime, it has to go along the walls of your box because it is bigger and bigger, so there is no space left. So there are regions here where it has to go very in the proximity of the wall. And again, years ago, we were studying this picture with Roberta Schottman. In those days, we didn't know other numbers than 1/2, so we were thinking that the fluctuations of that random object is still n to 1/2 at every location. But this is not true, and you have a question, and you also. Everything is known. The number of those droplets is 1. It's 1. I mean, the probability of having more than one droplet goes to 0 with n. If you want to know how fast that grows, this can be answered. Yes, sure. The length of that is also controlled, so everything about that is known. But I will tell you more. So all the data which is known can be found in the book by Roland Dobrushin, Kotetsky, and myself, which has the proof of this theorem. Okay. So then, what we said in our old paper with Roberta Schottman is not correct, and in fact, what is correct so there are two regimes for that random droplet. One is when it goes along the wall, and another one when it is free and it doesn't touch walls. So what happens here is that fluctuations here are exactly of the order that we are interested in. They are of the order of 1/3 and not 1/2. And here in the rounded part, they are fluctuating around this random shape. It is now somewhere here, and here the fluctuations are still as they were, n to 1/3. N to 1/2. Okay, so and next, what I want to tell you is the analysis that we were able to perform in the long paper written together with late Dima Joffe, Sebastian Ott, myself, and Ivan Vilenik. So this paper just appeared in Annals of Probability this year. So what we were able to show about the process here is the following. When you, as I told you, the fluctuations, the vertical fluctuations are of the order n to 1/3. And so if you take this random object here and you scale it vertically by 1/3 and you scale it horizontally by 2/3, So you squeeze it this way by n to 1/3 and that way by n to 2/3. What you would get in the limit, you take the limit as n goes to infinity, and what you find is called Ferrari-Spon diffusion. So the limit of that random polygonal line, when you do this scaling, in that limit, what you will get is some diffusion process. Okay, so this, you should think about this diffusion process in the following way. This diffusion actually lives on the positive semi-axis, so it is, it is like a Brownian particle living on the positive line in the potential, which looks like this. So there is some potential which can be explicitly described, and the particle is living there, and because of the hard wall at the origin, it cannot go to the left. So it's a diffusion process. You can write down the corresponding diffusion operator. I will not do this, but I tell you how to describe the stationary distribution of that diffusion process. So to obtain it, you should consider the Sturm-Liouville operator. So you take this differential operator on R1 plus with Dirichlet boundary condition. At the origin. Okay, and then you look for eigenfunctions of this operator, and those are obtained as follows. So you take the Airy function, which graph you have here. So this is the function. Okay, and then what you do, you take the first eigenfunction, which means that you just move your axis of your origin to the left, to the top, to the first 0. And if you do it like that, you obtain a function phi1. So it is just the Airy function, but shifted in such a way that it starts now at 0. Okay, and then, so you take this function phi1, and then the stationary distribution of this Ferrari-Spon diffusion is proportional to phi1 of x squared. Okay, so, and you can also write down what is the potential for that diffusion. So you know everything about this diffusion process. And in particular, because of the scaling I am telling you, of course, that implies that this random polygon indeed fluctuates by this exponent n to 1/3. Okay, so this is the main content of that paper here. So we already see some kind of KPZ normalization, but we don't yet see any trace of Tracy-Widom distribution. So to see more of that, we should go to three-dimensionalising model. And this is what we have to do. We now take three-dimensional Ising, and we put so-called Dobrushin boundary conditions, which means the following. We take a cube, and we then and then we split it into two halves. And we put pluses below here, and we put minuses here. And okay, so if we take those boundary conditions, then of course, at low temperatures, we will have plus phase below here, and then we have minus phase up there, and there is an interface which separates the two, okay? Now, what Roland Dobrushin proved in like 40 years ago, more than that, is that this random surface is rigid. So the fluctuations that it undergoes at positive temperature are just local. So you might see some bumps up and down, but they are just local. So if you sit at any given position and you try to understand where that interface, so you draw an axis here at arbitrary location, and then you see where your interface hits that axis. Then with high probability, it hits just at the origin. So the average height is 1, and the probability of being different from 1 is exponentially small in beta. So it's rigid. So on that, what you see is what people nowadays call gaseous phase. So it is the correlation decay on that random surface decays exponentially with local excitations. Okay, so, and then again we play the same game as before. From symmetry reasons, it is clear that the magnetization of a typical configuration in that box is, it's 0 in the first order, right? It is, okay, it is, definitely it is, yes, it is, okay, if you divide this by n cube, that goes to 0. Okay, because of the symmetry, you have some magnetization here and negative of that below, so the total is 0. So, and therefore, we now want to consider sigmas which have magnetization which is different from 0, but how much it is different, let me do it in the increments of n squared. So I will play now with the parameter a. A is positive, which means that I put inside more plus spins than are there on the average. Which means that, well, somehow this plus phase, which is below this interface, pushes the interface upward. The more A is, the stronger the pressure from below is. Okay, and then let me tell you on those slides there what we will see on that surface if we position ourselves here. So, and we look downwards. Okay, so this is our eye, my eye, and I'm looking on that interface here, on this random interface. And my eye is so focused that I don't see those local excitations. I only see objects of order n. And then let me tell you what will be that I will see. So I am looking from upstairs on that random interface. And initially, when A is between 0 and some A1, this is all I see. I will not see anything. It's just a square. There are just local excitations. As I told you, I don't see them. So that's the picture of what you will see when A is below a certain critical value A1. Now, when A becomes bigger than A1, all of a sudden you see some monolayer of plus spins. So maybe to be more precise, I draw it once more here, but in the three-dimensional case. So this is our initial interface, and then on it will sit a monolayer like that. So it is one atom high. It has certain area, certain shape. So it will be some random object. Again, with high probability, it will be just one single random, big random droplet. So it appears all of a sudden. It has already, so either you don't see anything or you see something of certain size. There is no intermediate size. Either there is nothing or is something of, say, of 1/4 of your box. So all of a sudden the monolayer appears, because see the extra particles, they push so hard, then this membrane cannot sustain them, and so it pushes it up, and then so that is what you will see. And then you increase A, and this monolayer then goes bigger. Okay, so, and then at a further moment, a second monolayer appears. It goes like that. This guy shrinks a little bit. It becomes something like that. And the second one is born, again of some size. And then both of them evolve. Initially, they evolve in such a way that that guy grows, and this extra one shrinks, till they would meet, something like that. And then they grow in unison, so to say. So just let me finish, and then I turn to you, and then I will answer your question. It is exactly true. Yes. In this regime, when we go from here to here, the external one shrinks, the internal one grows till they meet, and then they grow together. But it's life. I can comment on that maybe, but that's how things are. And okay, and then, as you correctly guess, there is then after you pass the A3 threshold, then the two of those together shrink a little bit, and the third one appears, and that goes on and on. This whole picture was obtained in our paper with the late Dima Joffe. I don't know, like 4 years ago or so. Okay, so say it again, please. Louder. No, it is not what happens. No, it's just the opposite. So the higher your level, the smaller it is. It never happens at the, well, see, with positive probability, everything happens. But typically, what will happen is that you have certain number of those layers. Each one is small. Each monolayer is smaller than the previous one, smaller or equal. With small probability, it can be otherwise, but this small, okay, it's small. Yes. Good. Okay. So let us make case steps like that, and stop, and then ask ourselves what we will see then. So imagine we have k of those. So this is my square seen from the top. I see several layers here. And I again look into this window. So I have k random polygons in there. And I want to understand what is it that I will see then. Okay, I will, again, I should scale in this way by a factor n to 1/3. And that way I should scale by n to 2/3. And in the limit as n goes to infinity, I will see a diffusion. In the chamber of the points, of k points. So on that set. So I am describing to you what I will see in that section. So that would be my x1, x2, x3, xk. So I have k intersection points. That's a point here, and so to say, this would be my time. As time goes, the random point here diffuses. Again, it is a diffusion in this chamber, and again, I can write down a diffusion operator of this k-dimensional diffusion, but I will not do that. But I will tell you what would be the stationary distribution of that diffusion. So we should take this more or less that same second order differential operator, the second derivative of dx I from 1 to k minus just sum of xi's, again, I from 1 to k. But we should consider that operator in this chamber, again with Dirichlet boundary conditions. Huh? Right. Okay. And again, one can write down the eigenfunctions for that operator in this chamber. And the eigenfunctions are readily can be read out from that same picture, but now we have to introduce other eigenfunctions of this one-dimensional operator. Namely, if we move the origin to here, that would be our function phi2. This will be our function phi3. So just the function phi1, phi2, phi3, and so on are just the same area function, but just moved with the origin moved correspondingly to here, 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 and there. And then the leading eigenfunction for that operator in this region with Dirichlet boundary condition is the following. You make the following matrix. You consider phi I of xj. It is k by k matrix. I and j run between 1 and k. So you have a matrix. Then you take its determinant. Then you take square of it. And this is the and then you should normalize it to make it into a probability distribution, and that density would be the density of stationary distribution of this k-dimensional diffusion in this chamber. Okay. This formula was obtained by Dima Joffe, Ivan Velenik, and Vitaly Vachtel. Okay, So you just have an explicit formula for the stationary distribution of the diffusion in this chamber when K is fixed. Okay, so the potential can also be written down as it could have been written in one-dimensional case. I will not do it now, but yes, there is some potential in this chamber which diverges as you approach the walls of it. So in the one-dimensional case, the wall was just 1 point, so there was a divergence at 0. Here you will have the potential diverging at the boundary of this chamber. And inside that, you still have, so to say, Brownian particle with living in that potential. Okay, so that's how much is known. And then I want to make now a conjecture, which is the following. So we have this k-dimensional distribution. In particular, we can integrate all particles except the largest one, the kth one, and then we get just a probability distribution depending on the parameter k. And now let us make another limit when n goes to infinity and number of trajectories also goes to infinity, so that the box becomes this cake of the number of pancakes that we have here also goes to infinity. And then we have the topmost one. And the topmost one, see the picture that we obtained here looks pretty much the one we saw yesterday. So we have here a gaseous phase with exponential correlation decay, and then it becomes another phase with power law decay, and there is this. It's not a. I wouldn't call it maybe Arctic Circle, because inside we don't have the frozen phase. We have the gaseous phase. So there is this curve here. The asymptotic shape of it can be written explicitly. That one. This is just a facet of the wolf shape in 3 dimensions. But what I'm talking about now is what are the fluctuations of the top pancake, the boundary of the top pancake, as the number of them goes to infinity. And my guess is that this should be the Tracy-Widom distribution, but so there is an explicit procedure, but what that explicit procedure gives, this I cannot state now. I don't know. But that's all I wanted to say.
Thank you very much for an interesting talk. Are there questions, comments?
I really don't know what to say. You should take n to infinity, and also k should grow. Maybe if k is constant, small constant times n, it would be enough. My guess would be that no matter how k, it should just grow. The number of layers should grow, and n should grow. K of the order of Cn with C small should probably produce this picture as well. Just the normalization would be different. Uh-huh.
Just some sort of pre-fermionic structure behind it. Is it the usual thing that people refer to when they say that we can associate fermions to the Ising model?
I think when people talk about Ising model and fermions, they talk about, say, 2-dimensional situation. So this is in 3D, and well, except that you see here a Slater determinant. So Slater, of course, means fermionic. So it is as fermionic as Slater is. So huh? Which is identical. So see, it's identical. Cannot, the answer couldn't be shorter. I would be very happy to agree. I do think like that, but I don't even know about the top one yet. But see, there are explicit formulas here. So once you have it, you then can study all possible questions if you are able to extract the information from this.
It seems that, I mean, if you first look at infinity and then you have this limit, then you could study that limit.
That's another way. Yes. I'm not saying that you should take the limit simultaneously.
It's probably harder to take them simultaneously.
So I am all yours to do to take the simplest. So sure.
Do you know anything about the numbers given in equation? Do you know them exactly, or do you have bounds?
You're talking about those constants here? See, they appear as solutions to some variational problem. So in a sense, the answer is yes. You just see you have the following problem. You have that number of extra volume you should incorporate, and then you look for the best way of doing it. So you can maybe increase. No, this already disappeared. You can either increase the density of pluses there and keep the interface like that, or else it costs more to build it, but at a certain moment you cannot stop. You have to. So you just solve your variational problem for every value of number of extra particles, and then you just from the variational problem you see all those pictures. So the answer to that is yes. We didn't study it. See, I doubt that. Because I was very fast telling about things here. All those, of course, depend on temperature. So they are, in fact, functions. So I would bet they are continuous functions in the temperature. So the answer to that is no.
If you try to reinterpret it, the same thing in terms of difference, which is reinterpretation.
See, in 2 dimensions, this is not a formula you get in 2 dimensions.
I mean those features. Formation of clusters, how the clusters place the boundary,
So you say we are in 2 dimensions. There is one big object, and we have this random shape. No, we never did this, and I don't see. It would be nice to see as the fermions would appear there, but I don't know. I don't expect this. So I would be happy you explain me that I'm wrong.
I don't know if there is something wrong, but I think I'm understanding is that this is concerning three-dimensional out of physicality.
Right. I am.
If you did the same game in which you are below, say, red, and
below.
Say that you do the same game with free call or box model. And
Oh yes.
You are
Oh, yes, yes, yes.
To agree,
Yes.
you would have similar wood shape and everything. So the heterogeneity of the fact that you have a threaded determinant just comes from the fact that the lines are contained one into the other, have nothing to do with Ising. It could have been the same with Cos.
Absolutely, absolutely. Yeah.
The big step is to reduce the complicated system into a one-dimensional quantum mechanics with a potential which is the absolute value of x on the real line. Once you have that,
Right.
the rest is all the quantum mechanics, in a sense. So
You mean
the
the study of this Schrödinger operator, so to say. This is totally correct. Right. So that does not depend on details. You would have same for the pods. I agree.
So that was just a comment.
Sure. I was talking about the Ising just to make things as simple as possible. You can once you see this picture, you can generalize it, but this is not what one should do in the talk. I agree.
Okay, thanks a lot.
Thank you.